Alright, for case one, we have a pool ball on a pool table and we're hitting it with a pool cue. The pool cue is hitting the ball parallel to the pool table. We need to figure out how fast the ball will roll and where we should hit the pool ball so it moves without rolling or without slipping. Our knowns are our centripetal velocity, it's constant, our change in time is known, and our radius is r. We use angular impulse, linear impulse. We also are assuming the force is greater than the friction between ball and table. Our assumptions are velocity is constant, the change in time is known, and static friction is negligible.
Good.
What? So what we are able to identify from this diagram is that we have to hit it at some point going from the bottom of the cue ball to the top of it. With this we will call h, you can also call it diameter, but we'll call it for h for this equation. We need to find out the impulse momentum of the linear force and also angular force. The way we did is that we had two equations that we looked up through the help of the wormhole. From there, we can also find out that the change in t, we can actually replace this with the change in t naught, which we were given at the beginning of the question. Since force is constant, that means the velocity is constant, so we can just change this to being the centripetal velocity. We can also do the same things with this equation, and we can solve for things. For the force average, it would just become force. So what we can do is that we could just write this as big force equals force times change in t naught equals mass times change in VC, or centripetal velocity. We can rearrange this so that we can find out what VC is, because we're going to be using this equation, which is VC equals R times omega. So then we just solve for it. Now we're going to work on the angular. For the angular, what we do is that we can actually make this sine theta just basically go to 1, because the force of it being hit, the direction, or R, with the force that's acting on it, in other words, the VC, is exactly 90 degrees. And 90 degrees on sine theta will make it 1. R, on the other hand, this R isn't exactly the radius, as it's actually the distance between some point to where the force is hit. And so the way we would do is that we would replace the R with h minus r, because it's going to be somewhere between the bottom to the top, and we can subtract r from that, so we can exactly identify where on the cue ball we're going to be hitting, so we can roll without slipping. So then we could rewrite it to being equal to force. With this specific F is actually going to be this. It's going to be exactly that. So we're going to, on this other side, this is equivalent. We know that the moment of inertia is equal to 2/5 mr squared. So we just do that. Omega. So now we solve for omega. So it'll be omega equal by 2 mr squared. We have now the centripetal velocity and omega. And so now we can plug them into this equation to find out exactly at what height would make this true. So you make both of these equal to each other, you'll get, going from what we got from here, you'll get R times 5, as we should do this, minus R over 2 mr squared. I know that's a big equation, but once we simplify it down, what we get is that at the height of 7/5 of the radius is exactly where we want to hit the ball so we can roll without slipping. Right. For case 2, what we're going to do is we're going to try to find out translation, rotation, and motion of the cue ball, and as well as we're going to try to find out exactly S, or the displacement that's going to be done while it's rolling without slipping. To do that, we're going to have to at least understand one of the kinematics equation, which is VC of T is equal to VCI plus A times T. The way we'll find A is that we know that the friction force is equal to mu kinetic times the normal force. And on this ball, the normal force and the gravity force are equal to each other. So we can rewrite N into just being mg. Turning this into mu k times mg. For acceleration, by dividing both sides by m, get rid of that. And so then this will now become VCI plus mu k g times t. And because it's slowing down, we'll actually be subtracting.
Okay, since Hugo solved for translational velocity, we're going to solve for angular velocity. And so we have our torque on a ball for the friction force, and we know that so we have the friction force times radius equals inertia alpha, and we know that that equals inertia alpha because the friction force times radius times sine, this sine cancels out and that equals 1. So it's just friction force times r equals inertia alpha, right? So now that we have that, we need to solve for alpha. So we go and we divide both sides by inertia. So we have the friction force times r over inertia equals alpha. And to solve for the angular velocity, we need the angular velocity kinematics equation, which is omega equals omega initial plus alpha times t. And so we know alpha, we just solve for alpha. So this is our alpha. We plug that in into the kinematics equation times t, and we have what omega equals. So we have omega equals initial omega, or omega initial plus the mu of k times mgr all over 2/5 mr squared, and then we times that by t. So to sum it all up, since we know that the friction velocity decreases while the angular velocity increases, we know that the centripetal velocity must equal the radius times omega.
We get that our angular acceleration is 5 times mu k times gravity divided by 2 times radius. Same process, but with angular velocity, and our initial angular velocity is 0. So we get this for angular velocity. So then we can use centripetal velocity is equal to radius times omega. Using Hugo's equation, we plug this in, and we plug omega in to get this equation, VCI minus mu k, gravity, times time, is equal to radius times r omega. We plug in what we got for initial centripetal velocity. We have to multiply this mu k times gravity times time times 2 over 2 to get like terms. We're solving for t, so we add this part to this part to get force times the change in time divided by mass is equal to 7 over 2 times mu k times gravity times time, and then we divide by this whole part to get t by itself. So mass goes towards the bottom. Then we have 2 over 7 times this whole equation, and we end up that our time is 2 times force times the change in time. It's 7 times mass times mu k times gravity.
Alright, so second part of the question, it asks us to kind of just find exactly at what point would it continue without slipping, just start rolling and keep going for the billiard ball. You want to find exactly S, or the translational displacement. So we're going to use this kinematic equation, which is v squared minus v naught squared equals 2as, and there's s in it, which means we can use it to find out displacement. We know v squared and v naught squared, which are another way of just writing the centrifugal velocity and the initial centrifugal velocity, because the initial means naught. We plug all these values into this equation, rearrange it so that we have this second term on the right side, and we simplify. What we also know is that these two are about the similar. Only difference is that this one is going to be 5. It's going to be 5/7, and this is just going to be 1. We can then kind of expand it, unfoil it, to the point where we get 25 over 49 minus 49/49. It gives us a negative 24 over 49 times the term, which is f times change in t naught over m squared. On the other side, it becomes negative 2 mu of kinetic times g times the displacement. We will then divide this term on both sides, so we have s by itself. At that point, it will become this, where it's at this point of distance is when it will just continue to go. In other words, it's after the time of 0 and the time we found, it will just continue to roll without slipping. First, check out the units, because that is an easy way to tell if all of it makes sense. And right here we got 7/5 r. R is a measurement of meters, and height is in meters. We're gonna do VC. VC is the same as is equal to force times change in time over m. F is equal to mass times acceleration. Time is seconds, and this is mass. These both cancel out, and if we were to go ahead and kind of think about the units of acceleration, units of acceleration are meters over seconds squared times seconds, which is the same as writing meters over seconds, which is the units of velocity. Talk about time. This 2 and 7 are just constants. They don't all play any part since they're unitless. And mass, since mass cancel out, so it'll just leave us with s. Time it also checks out, which is nice. So I'm gonna work on s, which is supposed to be meters, because it's displacement. This 24 over 98 is unitless, so is the mu k. So we can write those. But first we need to acknowledge that there's 2 kgs on the top and the bottom, which cancel each other out. It's weird. And this is the part that we acknowledge that now it's just meters, because these two cancel out, and so we're just left with meters. So now we have our displacements. This is one way to check that everything's correct, and so it is.
Another way to make sense of our values is we can change variables to be certain numbers, or we could say we're increasing or decreasing. The only one that doesn't really matter is our height of where the pool ball is struck. If you were to increase the mass, we would still have to strike it 7/5 of the radius for case 1. This answer also makes sense because we're not hitting it in the middle, we're hitting it somewhere up top, and that seems to be 7/5 of the radius. Another example is if we changed our mass to be 0. We can't divide by 0 here, can't divide by 0 here, and we can't divide by 0 here. If we were to increase our mass, let's say when we multiply it by 2, our ball would go 4 times as less. If we were to cut our mass in half, then the ball would go 4 times as far. And this makes sense because think of if you were to kick a soccer ball with a certain force. If you double that force, it goes twice as far before it rolls. If you were to kick it with half the force, it would go half the distance before rolling.
Okay, so for our reflection part of the project, we are going to use the example from our studio where the TA has a hula hoop, this thing right here, and they throw it that way, but they add rotational motion this way. So the hoop is rotating this way, but it's going that way. And why we're relating this to our problem is because of this equation right here, where velocity equals radius times angular velocity. And so what this means is that when they equal each other, that's when the hoop stops going this way and it starts going back this way. And how that relates to our problem is that we're trying to find, in the pool problem, we're trying to find when the ball is not slipping and it's just rotating. So